Hi everyone, this is Indu GEVEER, Assistant Professor at Rajasthan School of Engineering and Technology. So this is the fourth lecture on design of circular slabs and domes, Module 4 of Design of Concrete Structures 2. Now the next topic is conical domes. I already explained what a conical dome is. It is just as a shape of a cone, normal cone. And here also we have a meridional thrust and hoop stress. So if you look at this cone figure, you can see that there will be a meridional thrust along the inclined face of the cone. So this will be the meridional thrust. Meridional thrust, yeah. Then the hoop stress will be along the latitude, along the circumferential direction. This is the hoop stress H. Okay, so these are the two forces here also. Now let's consider the case of a conical dome subjected to an uniformly distributed load W as shown in the figure. So the meridional thrust can be derived to be T is equal to Wy by 2 cos square theta. W is the uniformly distributed load and Y is the distance of the point which we are considering from the apex of the cone. So this is the apex of the cone. This is the point P we are considering. And the point P is at a distance of y from the apex of the cone. So we are trying to find the meridional thrust at the point P. So at the point P, T is equal to Wy by 2 cos square theta. And if you want to find the stress, you just divide by the thickness of the dome. So Wy by 2T cos square theta. T is the thickness of the dome. We usually provide the thickness as minimum 75 mm for domes. So now when is the meridional thrust maximum? The maximum force will be when y is maximum. Here theta is a constant. So when y is maximum at the base of the cone. That means at y is equal to h. H is the height of the cone. So when y equal to h, the maximum meridional thrust occurs. And now let's come to the hoop force expression. The hoop force is H given by Wy tan square theta. Always it is having a plus sign. So always the hoop stress is compressive for a cone. Okay. Now for calculating the hoop compressive stress, you just need to divide by the thickness of the dome. Wy tan square theta by T. Here theta represents the angle as shown in the figure. So this is the angle theta. Okay. Now the maximum hoop compression, it occurs again at the base when y is equal to h, because y is maximum at the base. When y is maximum, you will get a maximum hoop compression. So it occurs at the base y equal to h. Now here also you have to provide a circular ring beam, because our horizontal thrust at the base will be inclined. So it will be like this, and this will have a horizontal component. This will try to push out the wall. The wall will burst outside, so outwards. So there will be a horizontal component. So to take care of this horizontal component, a ring beam. So this is the cone. So if this is the cone, a ring beam has to be provided at the base of the cone. It will be circular in plan. Okay, so this ring beam will be circular in plan. And the horizontal component of the meridional thrust will act like a force on the ring beam. This will cause a hoop tension force in the ring beam. Okay, so this ring beam has to be designed for this tension force. Now let's do a problem. Design a conical roof for a hall having a diameter of 20 meters. The rise of the dome has to be 4 meters. Assume live load as 1500 Newton per meter square and use M20 concrete and Fe415 steel. So this is the geometry of the dome. So it is given that this distance is diameter is 20 meters. So this base width will be 20 meters. Okay, and the height has to be 4 meters. Now first step is we have to calculate this angle, because this angle comes in all the equations for calculating the forces. So for calculating this angle, you can use directly the tan theta rule. So here this distance will be half of 20 meter, that will be 10 meters. So using tan theta will be equal to 10 by 4. So you can calculate theta as, we'll get theta as 68.2 degrees. Okay, the next step is assume the thickness of the dome. So the minimum thickness you can assume is 75 mm. So here I am assuming 75 mm thickness of the dome. Then calculate the total load. So dead load will be 25 unit weight of concrete into 0.075 thickness in meters. So the value is 1.875 kilonewton per meter square. Now the live load is given as 1.5 kilonewton per meter square. So the total load will be 1.875 plus 1.5 is equal to 3.38 kilonewton per meter square. Now let's calculate the forces. Now the maximum meridional thrust is at the base when y is equal to h. So let's calculate the maximum. We are interested only in the maximum values, right? So this will be when y equal to h. So W is 3.38 into 4 meters. Okay, y is equal to at the base. At the base we are calculating. So h y is calculated from the apex. Okay, so this is the y at the base. Y is equal to 4 meters divided by 2 into cos square 68.2 degrees, and the value you get is 49 kilonewton per meter. Now we got the force, right? Now we have to find the stress. Okay, so the stress will be the meridional stress. Okay, that will be T max divided by thickness. Okay, so that will be 49 divided by 0.075. That will be 653.3 kilonewton per meter square. Now you convert into Newton per mm square, you will get 0.653 Newton per mm square. Okay, now this value of stress should be less than the allowable stress in concrete. So the allowable stress or the permissible compressive stress direct for M20 is, we already seen in the last problem, it is 5 MPa. You can take it from the IS 456. So this value is less than 5 MPa allowable limit. So we are on the safe side. Now let's calculate the hoop stress, hoop compression. We already discussed that throughout the cone there will be compressive hoop stress. Okay, so the maximum hoop compression will be at the base wherever the y is maximum. So the maximum, let's calculate the maximum value. That means y is equal to h is equal to 4 meters. So now the load we have already calculated 3.38 into y is equal to 4 meters into tan square 68.2 degrees. Okay, so you get 84.5 kilonewton per meter. So this is a force. Now for calculating the hoop stress, you just need to divide by the thickness of the dome. So thickness is 0.075. So you get a value of 1126.6 kilonewton per meter square. So this, if you convert into Newton per mm square, you will get 1.13 Newton per mm square, and this is less than 5 Newton per mm square. This is the permissible stress in concrete, compressive stress in concrete. So it's okay. Now we have to provide some minimum reinforcement in the dome, that is 0.12%. Reinforcement 0.12% by 100 into 1000 for 1 meter into the thickness of the dome, that is 75. So you get about 90 mm square. So provide minimum reinforcement 8 mm dia and 300 mm center to center. Similar to that we have seen in the dome. This is the primary advantage of a dome because we need only minimum reinforcement in the dome, because primarily the stresses are axial forces alone, that too compressive. Okay. Next we are going to see the ring beam design. I already discussed that we need a ring beam design at the base of the cone. This is to take care of the horizontal component of the meridional thrust as the base. So we already calculated the meridional thrust as the base. This will come as on the ring beam. This will be the meridional thrust and the horizontal component of the meridional thrust T max into cos this angle. Okay, cos theta 1. Let it be cos theta 1. Okay, will be the horizontal component. So what will be this theta 1? So if you consider the geometry of the dome, you know this is theta. So the thrust will be in this direction. So if you consider this right angle triangle, this is 90 degrees. So this angle will be 90 minus theta. So the horizontal component will be T max cos 90 minus theta. So that is what is written here. The horizontal component will be T max into cos 90 minus theta. Okay, so we have already calculated the T max, the meridional thrust at the base. So the value of that is 49 kilonewton per meter. So considering the horizontal component, this will be 49 into cos 90 minus theta, that is sin theta. So sin 68.2 degrees. So you get a value of 45.5 kilonewton per meter. Now this is the horizontal component. Well, this will act like a pressure on the ring beam. So on the plan, the ring beam will look like this, and this will be the pressure on the ring beam. So that value is 45.5 kilometer per meter. And to find that, there will be stresses in the ring beam due to this. So stress will be tensile in nature. This is called hoop tension in the ring, and that can be calculated as P by 2. P is the horizontal component, is 45.5. And the diameter of the ring beam, this one will be again that is given to you in the question. It is the base width, that is 20 meters. Okay, so this will be into 20 by 2. So that will be 455 kilonewton is the force hoop tension in the. So next thing is, we already know, we have already calculated this. First you calculate the area of steel. Okay, so for calculating the area of steel, you know the allowable stress in steel, that is 230 MPa from table 22 IS 456. Again I'm repeating, we are doing the working stress method of design. You have to look at the annex B of the code. Okay, so there you have the working stress method of design. You get the permissible stress in steel. Okay, now from permissible stress, you can calculate the area of steel. See, force equal to stress into area. So area will be equal to force by stress. So that is equal to, we know the hoop tension, that is 455 kilonewton. Okay, you convert into Newton into 1000. Okay, this 455 is in kilonewton. So into 1000 divided by 230. Okay, so the area of steel required is 250 mm square. Now you find out the number of bars required in the ring beam, that is equal to area of steel divided by area of 1 bar. Okay, let me assume 22 mm diameter bar. So pi by 4 into 22 square will be area of 1 bar. So you will get 5.2, approximately 6 bars. So provide 6 bars of 22 mm diameter in the ring beam. Now let us find the area of cross section of the ring beam. Okay, so once you get the area of steel, you can find the equivalent area of concrete. Okay, that is A plus M minus 1 ASD. Here M is the modular ratio. Modular ratio is the ratio of the Young's modulus of steel to the Young's modulus of concrete, but the code gives a formula to calculate the modular ratio. We calculated 280 by 3 sigma CBC. So that value we already got in the last problem as 13.33. So from here we can calculate the equivalent area. That will be A plus M minus 1 will be 12.33 into ASD. Now ASD we already know ASD is equal to 6 bars we have provided, right? 6 into pi by 4 into 22 square. So the area of steel we can calculate. By substituting this, you will get the equivalent area as A plus 28122.2. Okay, so we got the equivalent area. Now the condition is the stress is equal to force by area. We know the force is the hook tension. Hook tension is the force. So 455 into 1000 convert into Newton divided by the equivalent area. Okay. Now the stresses here, the hook stress is tensile. Okay, the force is tensile in the ring beam. Okay, it's very important. This is called the hook tension in the ring beam, not in the dome. Okay, in the ring beam you have tensile stress, and that tensile stress should be limited to the permissible limiting stress in concrete, tensile strength in concrete. So this should be less than the 2.8 MPa. Okay, so from this condition we get that A should be the area of the rectangular section should be greater than 376257.8 mm square. Okay, so now provide provide 650 by 600 mm ring beam. By providing that, you get an area of the 390,000. Okay, so that we satisfy this condition. Okay, so provide a ring beam of size 650 by 600 mm and provide 6 bars of 22 mm diameter. Now let's do the detailing of the conical dome. So let me draw the dome first. Okay, and this is the ring beam. Ring beam size is 650 by this is 650 and 600 mm, and you have to provide 6 bars of 22 mm diameter in the ring beam. Okay, so this is the 6 bars and provide a stirrup also to link the 6 bars. So 6 22 mm dia bars and the link is 8 mm dia at 300 mm center to center. So nominal reinforcement to tie the main bars. Okay, now you have to provide the reinforcement, that is minimum reinforcement we provided, that should be the middle of the thickness. So you provide a minimum reinforcement. We got the reinforcement as 8 mm dia at 300 mm center to center. So this also, this reinforcement will be in the meridional direction and this will be in the latitude direction, that will be 8 mm dia at 300 mm center to center. So with this we have done a problem on the conical dome and the spherical dome. So with this our module 4 and ends with this. Okay, thank you everyone.